All right, well, I think we can get going here. I'll introduce the group. So, my name is Blake Bonham. Welcome to our Dorsey Power Hour on energy recovery. We got our three other sales engineers, Scott Boucher, Chris Wooldridge, and John Neeson in our Seattle office. And today we'll be, like I said, talking about energy recovery. Our presenter is Jordan Locher. He's been an application engineer with Greenheck for quite some time, and so he's familiar with our Washington State requirements. I will be a couple housekeeping things. I'll be muting everyone just so we have a clear audio. But if you have questions, please enter them into the chat, and we can answer them at the end. Or if it's fit, we can answer them when we in real time. So with that being said, Jordan, you can take us away.
Awesome. Thanks, Blake. So like you mentioned, today I want to talk about how about that?
Sorry, I muted you. Sorry.
Okay, so afternoon, everybody. My name is Jordan Locher. As Blake introduced there, I'm going to talk to you guys about energy recovery, and specifically for the Seattle and Washington markets. You guys are definitely at the forefront of some major changes related to energy recovery. So we'll definitely dive deep into those and talk about how that affects using energy recovery equipment. So just a little bit about myself. I am an application engineer at Greenheck, specifically in our tempered air products group, where we focus on energy recovery ventilators. I've been back with Greenheck for a couple years now, and I actually was an engineering co-op with them just over a decade ago now. We're going to focus on today, so I'll go over a high-level energy recovery overview. Hopefully everybody's familiar with it and kind of what are we doing with energy recovery. Then we'll jump into the energy recovery technology. So we'll talk about both wheels and cores and what you might see in the market. I'm going to cover frost control. That's usually a pretty big topic for ERVs. Then we'll go across the Greenheck products and what we offer. And then we'll get into the meat of it, the Washington State Energy Code and what's been updated. And then we'll sort of finish off with what we can do to improve using ERVs and ERV performance.
Hey, Jordan, I think the slides are not going.
Okay, you guys only see one?
We're not seeing the actual slideshow. We're seeing your slides, like in editing mode.
Hold on. Sorry about that.
Good.
Switch this guy over. I'm updated. Okay, we'll just run with this then. I can get it to switch. Is that full screen?
Yep, perfect.
Yep.
Okay, awesome. So what is energy recovery, right? So the whole purpose here is we're utilizing that space neutral building exhaust, right? We paid a lot of money to condition that air in the space. So why not capture as much of that outgoing energy before we send it out the door and use it to precondition that incoming fresh outdoor air, right? So help reduce that temperature and humidity and a lot of cost savings and energy reduction that comes from that. So the whole point, right, is we're trying to reduce that outdoor air load. And then as a good rule of thumb, typically with an energy wheel, you can save around 3 to 4 tons of cooling per 1,000 CFM of outdoor air, whereas typically an energy core is a little bit less, around 2 to 3 tons per 1,000 CFM. So I always like to point out this slide, so we call it the HVAC dichotomy, right? So where are we at in the industry? So coming out of the pandemic, right, there was a lot of ideas and trends and what can we try? How do we mitigate, harmful bacteria and viruses in our air? Really, the answer that I think everyone has agreed upon is we should increase our ventilation to the space, right? So getting more fresh air into the building is a good thing. However, the flip side of that, right? How does this impact climate change? How does this impact our overall building energy usage, and how can we reduce that usage? So really, energy recovery is the key technology here in the middle that's going to help do both. And that is why, we're talking about it, and the code regulators are really pushing this technology wholeheartedly, because it does make a lot of sense. So how does this technology work? So this would be a typical equipment. So this example is using 4,000 CFM of outdoor air. During the summer, on a hot and humid day, we're bringing in that raw outdoor air, 95-degree temperature. We're going to cool it down. Typically when we talk about this DOAS ERV type application, we're looking at full dehumidification. Right, so driving down to a 50, 55-degree set point. To handle that much outdoor air without energy recovery would take around 32 tons of cooling. However, if you were to use an energy wheel for this exact condition, you can see now we're on that green line. We'll significantly reduce that tonnage requirement, and now we're down to around 16 tons. So almost half the cooling capacity just by using energy recovery. The other big thing that's important here is using energy recovery is going to help reduce the variability of the outdoor air conditions, right? So typically you're dealing with a wide envelope of conditions. A lot of times ERV can reduce that, helps reduce that system cycling, right? A lot of benefit there as far as the complexity of heating and cooling. I'd say specifically, for your guys' Pacific Northwest climate, this is a huge deal, because a lot of times you can see bringing that outdoor air load down to that kind of green comfort zone. A lot of times just using energy recovery can help us avoid tempering altogether, right? It might be mild enough that we can supply preconditioned air to the space without needing tempering at all. And so the big term here that we're going to mention a few times throughout the presentation is ERR, or enthalpy recovery ratio, right? So this is what it looks like. It's just a ratio of our change in enthalpy of our supply air over our change in enthalpy of our return air. Right, so you can go through, you can calculate it, right? This is based off those conditions I just showed you, plug in all your numbers, and then basically it'll tell you based on the ERR number you're trying to hit, what does the enthalpy of your supply air need to be. So I have it highlighted there, that 50% number. We'll kind of talk about that again at the end of the presentation here, is it is something that has changed. Another important term you need to be familiar with for energy recovery, it's commonly called cross leakage. The technical term is EATR, or exhaust air transfer ratio. Basically, that's the amount of the exhaust air that might leak over to the supply side of the cabinet. So it's just something we have to pay attention to using ERV. The reason it's important, right? So ASHRAE 62.1, it does define, based on the class of air we're handling with that energy recovery system, what the maximum EATR is allowed. So you can see here a class 1 air, clean, not offensive, go ahead, not a big deal. Class 2, that's one of the more common ones, right? A bathroom exhaust, we have to be less than 10% EATR. And then class 3, this is that slightly more hazardous. A good example might be a vet office, nail salon, janitor's closet, something like that. You have to be less than 5%. And then typically class 4 and above, right, that is a 0%. We can't allow any leakage whatsoever. So talking about energy recovery technology itself, so we'll talk about wheels first. right? So the way that energy wheels work, typically these are a counterflow arrangement. So you can see that supply air goes on one side of the wheel, and then our exhaust air is going to pass by on the other, and then that wheel is going to rotate between those air streams. Typically, the wheel matrix, right? So that's what the wheel material is made out of, is going to handle that sensible energy transfer, transferring our heat. And then typically we're using a desiccant applied to that wheel to transfer the latent energy or the moisture side of it. So if you've never seen them before, it looks like this. You can get this guy to play. Maybe not. But typically this would be summertime conditions, right? So we're going to bring in that hot and humid outdoor air. We're going to reduce that temperature and moisture from our outdoor air and use our relatively cool and dry return air from the space. In the wintertime, it works exactly opposite. So now we're bringing in cold and dry air, and we're returning relatively moist and warmer air. We're actually going to keep that moisture in the space in the winter, which typically is a benefit as wintertime tends to see our spaces drying out. So it works great in the winter as well. As far as the types of wheels that you might find out in the industry, so the two most common ones are going to be an aluminum wheel or a polymer wheel. So both of these wheels, they are very, very effective, right? So you can see that ERR number, typically 70 to 80%. It's pretty easy to push them past that, right? You might even be able to squeeze up to 85% out of them. One of the biggest differences between aluminum wheels and polymer wheels is the thickness of that wheel. So to get that same 70 to 80% energy transfer, aluminum wheels are usually in that 6 to 12-inch thick range, whereas our polymer wheels, we have both an 1.5 inch and a 3-inch offering. So quite a bit thinner. Another big difference is our polymer wheels usually are a segmented design. So we have these kind of pie piece shapes that you can use on the energy wheel. It's very easy to take those pieces out, clean them, maintain them. It's a very straightforward, simple process. Whereas a lot of times those aluminum wheels are a one-piece wheel. So they get a lot bigger, a lot heavier, and a lot bulkier and harder to deal with. There is a difference between the desiccant. So you can see here the aluminum wheel uses what's called a molecular sieve. It's like a sprayed on coating, whereas Greenheck, we use polymer wheels with a silica gel desiccant. So we'll talk about that. So basically the differences between the two, that silica gel desiccant, you can see this picture here. It's a microscopic image. It is a permanent coating, right? So that desiccant is permanently applied. This means you can wash it, you can clean it. The wheel is going to last the life of the unit, right? So there's no degradation of performance. It's a very robust, simple design of a wheel. Whereas in contrast, that aluminum wheel, like I said, it's that sprayed on coating. You can see there, typically to clean those, a lot of times people will pressure wash them. When you tend to pressure wash those aluminum wheels, it can actually flake off and degrade that desiccant. So at the end of the day, the polymer wheels, really a great option there. And then you can see cleaning wise, basically low pressure water, soap detergent, right? So very easy to clean and wash. So the flip side of using an energy wheel would be an energy core, right? So we do see in the ERV market around 50 to 60% can have a preference for cores over wheels. Typically, this is going to be in the lower airflow ranges, right? So less than 2,500 CFM. Anytime we're above that 2,500 number, we tend to see a pretty strong preference for wheels. So the biggest difference between wheels and cores, so right, the core is a static device. So it has no moving parts or pieces. It's a very simple design. The way it works, you can see this image here. Basically, it's a stack of fluted plates. Each one of those fluted plates is set at 90 degrees to each other, and then those airflows are allowed to pass over each other in the core. So it transfers both temperature and moisture across those plates. But the big advantage of it is it has very low cross leakage, right? So there is a physical divider between those air streams that prevents the air from leaking from one side to the other. Just as a note, you might hear a lot in your guys' market, the term HRV versus ERV. So typically an HRV is a heat recovery or a sensible only device, whereas an ERV is enthalpy recovery, meaning we're going to recover moisture. So this is what it would look like on a core in the winter. I apologize, can't get this guy to run, but so basically, you'd have your outdoor air coming in that top right, going across the core and supplying to the bottom left, and then returning on the bottom right, going across and exhausting on the top left. So it works the exact same way as the wheel. It's going to transfer both that heat and that moisture. And then, like I said, in the winter, it's just the exact opposite, right? So Greenheck, we do offer two different types of core material. These are two of the more common ones that are out in the market today. So there's a fiber membrane core or a polymer membrane core. So the differences between the two, typically that fiber core, essentially fiber, just a fancy word for paper. So it's a paper type core, whereas that polymer is a plastic core. A lot of competitors in the market are only going to offer that fiber membrane type core, whereas for Greenheck, we actually offer both. So the differences between the two, performance-wise, you can see the ERR number is definitely lower than a wheel. So our fiber cores range in that 50 to 60% number, whereas our polymer cores, we can usually squeeze about another 5% out, up to around 65%. That EATR number or cross leakage, like I said, it's very low, typically 1% or less. So I would call it practically zero, not quite zero, but very low. And then the biggest difference between the two is going to be the cleaning, right? So that fiber core, right, it is just a big paper core. You can't get it wet. If it were to get wet, it would get destroyed. So that is like a vacuum only type core, whereas that polymer membrane, now that is a washable core. So very similar to the wheels. Like I said, here you can see just, example of using that garden hose versus vacuum cleaner. Typically, it's around 5% increase in performance. And across our core models, we can usually push that airflow performance a little bit, right? So depending on the cabinet size, there is an increase in airflow by using that polymer core as well. So I want to touch on frost control, right? So it does depend on your climate. Coastal Washington, Seattle area, I doubt frost control is really too big of a concern. But if you are working outside of the city and in different job sites, you do have to pay attention to frost control, right? So if we have a cold enough outdoor air temp, we may require it. It is also very dependent on the relative humidity of the space that we're exhausting from, right? So typical applications, we're going to be less than 35% RH in the winter. So anytime you're dealing with a job that has extra humidity coming from the space, I say the perfect example of this is like a locker room with some showers, right? That's a situation where we know there's going to be a lot of extra humidity coming to the device in the winter. So you might want to consider frost control at that point. And then the last one on there that determines how often we need it is how effective the device is, right? So the more effective the device is, the less likely it is to freeze. What happens if we do nothing and don't think about frost control, right? So if it does start to frost up the device, we could lose that airflow. A lot of times these ERVe or DOAS units are supplying that code required outside air, so you might not be getting that. And then also we're going to reduce that effectiveness and that energy savings, right? So it might not be performing optimally. So if we need it, definitely want to consider frost control. I just want to make a note here. So this chart kind of shows you the difference between an ERVe and an HRV, right? So I know HRVs are pretty popular in your guys' climate as a sensible only device. One of the biggest things to watch out for with an HRV is you can see here that red line. Because it's a sensible only device, it's very susceptible to frost. And typically we see HRVs spec'd out on jobs with very large preheaters, right? So they use a lot of extra energy to prevent frosting up that HRV. Whereas you can see on that blue line, if you use a total enthalpy core, you're going to avoid frost significantly more. So as far as frost control goes, it's definitely a benefit to use an ERV over an HRV. And then just a handy map here. So like I said, most of coastal Washington, probably not a big deal. But as you move in, you might want to consider it. Some of the options that we offer at Greenheck, right? So you could have no frost control. It's relatively warm. Timed exhaust is one of the simplest strategies we have. Basically, the idea there is if we detected a frost condition, we're going to periodically shut down the supply fan. So stop bringing in that cold outdoor air and only run the exhaust fan, right? Very simple solution, not a lot of cost, not a lot of hardware. But obviously, the downside there is you're periodically shutting down that supply fan. If it's a bigger concern or a colder climate, then we would recommend going with an electric preheater, right? So the idea there being it's just too cold, we'll add a little bit of energy to that incoming outdoor air and keep the device running optimally and at full effectiveness. Right, so between wheels and cores, we offer both timed exhaust and electric preheat on both of them. Right. So one thing I'll point out with electric preheat is I think it's a common misconception that, this is the type of thing where it turns on in November and it runs through April or whatever it might be, right? We're only running the electric preheater when we absolutely need it, right? So when it is a frost condition. And then the last one that we have as an option, if you do go with an energy wheel unit, we also have an option for modulating wheel, right? So the idea here is we would slow down the wheel. That would allow that wheel more time to get exposed to that warm exhaust, and then that would act as our frost control. Really great option there. Not a lot of cost and really hardly any downsides to it. So if you're going with a wheel, definitely a great frost control option. On the summer side of things, so as far as economizers go, right? So there is a difference here. So one of the downsides of using an energy core is it is a static device, right? So we can't turn off or disable the core. So for cores, we actually have to use a physical bypass damper as our economizer, right? So the idea there would be if it's an economizer temperature, we're going to open that damper and bypass the core. However, with a wheel, we can actually stop, jog, or modulate that wheel, right? So because we can control the speed of it, that counts per code as our economizer. So if you didn't notice there, that modulating wheel, it's a great 2-for-1. Adding that cost to the VFD gets you both an economizer and frost control in the same bucket. And then the last one that's on there, exhaust only. This is pretty common. If you do have this ERV tied into some downstream equipment, say a downstream air handler already has an economizer, right? You might only want to use the exhaust fan during economizer. So just an option there. Okay. Now we'll get into our Greenheck products that we have for ERV. So we'll start off on the core side of things. So this is our MiniCore unit, right? So kind of a small, 1,000, maybe 1,200 CFM unit. These are very, very versatile units. So indoor only. You can see here, whether it's in a vertical orientation or laying down horizontal. We do offer these with both a base mounting kit or a hanging kit. So very, very flexible design of an ERV here. Basically get it in just about any situation or space you need. We have two different cabinet sizes. So we have a MiniCore 5 and a MiniCore 10. Roughly about 500 CFM on the 5 and about 1,000 on the 10. Can go a little bit higher than that. And then both of these are available with either our fiber or our polymer cores. So it is a AHRI 1060 certified. It's going to be the same as all of our ERVs. And then any of our smaller ERVs, we actually use our very green EC motors, right? So very efficient motor technology. And we'll actually kind of hit on that a little bit later here in the presentation. If you do need a larger core unit or maybe an outdoor mounted core, so we also have our ECV line or energy core ventilators, right? So you can see here we have 4 different sizes, the 10, 20, 30, and 40. Basically, that is the number of cores that are in the unit, right? So between a 1 or up to a 4 core unit. So you can see that picture in the top right corner. Like I said, these can either be indoor or outdoor mounted. And then the nice part with these units is really we have all of our controls options available, right? So we can hook them up to a BMS. We can put a microprocessor on it. There's a lot of different controls, sequences, and options that we have available. So they're very, very flexible units. There's a lot of different ways that you can control this equipment. In our smallest size there, you can see the ECV10. It's going to use the very green motors. And then once we get into the larger ones, it is a direct drive plenum fan with a VFD. So then if we flip over to our wheel units, so we do have, this is our smaller indoor wheel. So it is the MiniVent. 2 sizes in this cabinet, so a 450 and a 750. So, almost 500 CFM and almost 1,000. Same thing as the MiniCore, right? Very flexible unit. The ductwork actually has some blank off panels on it. So once you get into that space, whether it's hanging or base mounted, you can actually see on that picture, there's 2 openings on both sides of it. So it's very easy to adjust that ductwork and make it flexible in the field. So the really cool part with these MiniVents is even though it's a really tiny wheel unit, it's still a 70 to 80% effective wheel. So you're still getting that high energy transfer of a wheel, even though it's a nice size package. And then we have our larger wheel units, right? So we have 2 different models, the ERV and ERVe, right? Kind of depends on whether you want them indoor or outdoor mounted. Really wide range on the wheels, right? So we can go anywhere from 300 all the way up to 12,000 and just about anywhere in between. So very flexible there. There are 2 different wheel thicknesses. Like I mentioned at the beginning, there's an 1.5 inch wheel and also a 3-inch wheel available in these models. And then similar to the ECV, right, we offer full controls on these. So microprocessor, BMS, frost control economizer, right? There's a lot can be done there. And then if you do need tempering, right, we do have a full DOAS lineup, right? So this is integrated heating and cooling. So whether it's our RVE with a wheel or RVC with a core, right, we do have a full line of DOAS products with different heating and cooling options as well. So, okay, I might take a quick break here. Are there any questions up until now?
Not
I just
seeing
want to
any
pop on.
questions.
Yeah, I just
Go
wanted
ahead,
to
Chris.
say, yeah, that we'll be doing a separate RV, RVE, RVC presentation here in a few weeks. So be sure to check the Power Hours schedule, and we're going to dig into some of the DOE compliance changes and the refrigerant change coming up on that particular product.
Yep. Yeah, just wanted to mention that out there. So. Okay, so I'll keep going then. Okay, still full screen.
You're good.
Okay. Okay, so I highlighted all of Greenheck's ERV products, right? So kind of what we're doing with it, why it makes sense. Now I want to shift focus a little bit here and talk about the new Washington State Energy Code. So to get very specific, right? So this is the 2021 code update. Covering the commercial side, right? So they did split it out, residential and commercial. There's quite a bit more to the residential side as well. And then I believe this code, it's gotten delayed quite a few times, but I think from everything I was reading, it has finally gone into effect just this last month here. So we're going to go through and talk about what these changes are and what it affects as far as an ERV or DOAS type system. Right, so the major takeaways from the new Washington State Code. So these are what you have to be concerned with as far as selecting a DOAS unit. So we have a new and increased minimum ERR, right? So they've now moved that ERR to a 60% number. Previously, it was 50%, and they also had a sensible only requirement. So the new Washington code has adopted this 60% number and focuses more on that ERR or a total enthalpy number. There's also a new requirement for fan power, right? So that requirement is 1 watt per CFM or less. We'll kind of go through and talk about that. In general, I would just say there's a much higher focus on using a fully decoupled DOAS system. So I'll kind of touch on what that means. And then they also did write in some language related to a high performance DOAS option, right? So where that applies, we'll talk about what it takes to kind of hit that. So talking about the new minimum performance, right? So like I said, they raised it to 60%. So you can see that ERR calculation that I showed you earlier. So now when we're doing this calculation, we have to hit a minimum of 60%. What does that mean? So I mentioned wheels typically are 70 to 80%, and cores are typically 50 to 65. So what you might notice here is basically, half of that core range is kind of cut off with this new code. So the easiest way I could describe that is if you're using a wheel, you could have, it's pretty easy to hit it with a wheel. You could have a rather sloppy design of a wheel and still be above 60%. Whereas now, if you're using a core ERV, you have to have, a good design, a tight design, and make sure we're optimizing the performance of that core in order to hit that minimum 60%. So just be aware of that change. It is going to have a little bit of a shift in thinking and how we design using ERVs. So on the fan power side, right, so now we have this rule requiring a 1 watt per CFM fan power. So basically what that means is the combined power of both supply and exhaust motors have to be considered. And then that's based on the CFM that we're using on the unit. The good news is, Greenheck, we were aware of this change, so we've gone through on all of our ERV products. We've tested them all for fan power, and we already have that information built into our selection software. So if you've never used it before, we have it available in both our full-blown caps or also e-caps, our online tool. And then it's also going to print out in submittals on these units. This is just a screenshot here from e-caps. So if you've never seen this before, you can add the fan power metric. So as you know, whatever metrics you have displayed across here, there is this gear icon in the top right. That's your settings. You can go there and there is now a selection for fan power. So you can add that metric in there and you can actually sort it by fan power if that's your key target. So it is really helpful, very easy tool, kind of shows you just to make sure, hey, am I selecting a compliant ERV product? Like I said, because we use our very green EC motors in a lot of our smaller ERVs, we do have, very good fan power performance. You can see here, just on how I selected one of these MiniVents, a lot of times it can be lower than half a watt per CFM. So what does that whole decoupled DOAS mean, right? So the focus here and kind of the intent of the Washington State Code updates is to drive, especially new buildings or any HVAC replacement towards considering or using this decoupled DOAS approach, right? So DOAS meaning a dedicated outdoor air system. In this case, I have it shown with heating and cooling, but the same applies if it's just an ERV without tempering. But now we're going to be preconditioning that outdoor air, getting that energy recovery benefit, right? Pulling our relief air and our bathroom exhaust, and then supplying that preconditioned air directly to the space, right? So the key here is now these are a decoupled system where that zone tempering is handled by a separate cycle, whether it's an air handler or a terminal unit, and then your ventilation air is its own decoupled system, right? So there's a lot of advantages to that. Greenheck offers a lot of equipment that can help you out with that, and definitely have some more insight on that. And then I do want to highlight, so they did build into the code this high performance DOAS option, right? So, depending on how you're designing your building, this could be either with a standalone energy recovery as your DOAS, or with a packaged unit. But basically the requirements for this are tighter than the standard requirements. So now in order to hit this high performance option, you'd have to hit a minimum of 80% sensible recovery. And then that fan power to hit this option would actually have to be less than, just about 3/4 of a watt per CFM. So the reason they did this is basically they're going to offer you design credits and incentives by using a higher efficiency DOAS system. And either way, Greenheck has a lot of great options that can help you hit this target.
Hey, Jordan, quick question.
Yep.
We had a question in the chat on the code before this. Mike asked, does the listed watts per CFM include both the SF and the RF in the total? That was, I believe, on the couple slides before this.
Sure. What are we referring to with
Yep, right there. I think the supply fan and return fan.
Oh,
correct.
supply.
Watts
Okay.
per CFM.
Yes, yeah. So watt per CFM is considering both the supply and the return fan in that calculation. The one that is different on a wheel unit is I don't believe the wheel motor is included in that. However, we're aware of that per code. We don't have to include that. And in general, I think a lot of people get really concerned about wheels, that somehow the wheel motor is sucking up a lot of power. I can tell you typically those wheel motors are very, very tiny and a very insignificant power consumption on a wheel unit.
Thanks, Jordan.
Awesome. Okay, so we went through the major updates for the new Washington code. So now I want to kind of talk about, so, okay, we have these new codes. I'm used to designing with ERV. How is this going to change? How am I going to improve how I'm selecting ERVs to accommodate and meet this code? Right. So there's a couple big takeaways here. So what can we do to improve? Right. So I'd say the number one thing that's changing with the implementation of this code is we need to make sure we're doing a proper design. Right. So we can't be sloppy. We'll talk about balanced airflows is really the key there. Uh, the next one is going to be ERV oversizing. So that's the big trend there where now instead of, if it was 1,000 CFM cabinet and we're going to push 950 through it, maybe think about going to the next size up, like a 2,000 CFM cabinet, pushing that same or lower airflow. There's a lot of benefits for there, right? So that's going to help increase that ERR and then also lower that fan power. So we'll kind of go through some examples. And then the last one is just the design of the ERV, right? So there's a couple options we can pick there. I talked about the difference between that polymer and fiber core, and then driving towards using a higher effectiveness wheel. So if we talk about proper design, right, the most common thing I've seen from the ERV market is dealing with unbalanced airflows, right? So that ERR number is directly related to the amount of exhaust air. So the best design is a balanced design, right? So 1-to-1 outdoor air is equal to exhaust. I'd say it's pretty common, a lot of times we'll see a little bit higher outdoor air just to keep that building pressure 90% or higher between the outdoor air and exhaust is pretty common. But what happens is you can see on this chart as you lower that exhaust airflow ratio, that ERR starts to drop dramatically, right? So this example, rather large unit, a 9,000 CFM unit, you can see at a balanced airflow, we're looking great. A little bit of an unbalanced, still pretty good. As we go down, now we're dropping below that code minimum 60%. So it is very, very critical to get enough exhaust to these units, especially on the smaller ones. If it's only a 1,000 CFM unit, 100, 200 CFM of exhaust can make a world of difference, right? So in the design of it, whatever that means, if it's pulling in one more bathroom or one more return duct, it can make a really big difference to meeting that code compliance. And then I talked about ERV oversizing, right? So here's an example, right? Two different selections. So looking at our wheel unit, let's say we were looking for an 1,800 CFM wheel. So our ERVe model, this is an outdoor wheel unit. You could go with that ERVe-20, so a 20 size cabinet. However, with the same exact airflow, if you jumped up to our 35 cabinet, that's around a 5% increase in ERR. So like I said, increasing the cabinet size, there's a little cost involved, but we're going to make that up by increasing the overall energy performance. So you can get better payback. And then we'll see a lower watt per CFM number as well. Another way that you can improve it, right, is going between that polymer and fiber core, right? So for this instance, I looked at a 3,100 CFM core unit. You can see jumping between the two, 5-6% difference. Whereas on a smaller unit like that MiniCore, a 300 CFM unit, there's actually around a 10% difference. I would say in general, what we've seen with cores is typically they perform much better when you try to push less air through the core. They're a lot more susceptible. A wheel you can typically push a little higher on the airflow range, and there's not as dramatic of a drop in performance. Whereas the cores, the further and further you push them, that performance really starts to drop off. So the big takeaway is if you are considering a core, you're gonna have to think about less airflow through that core. And then looking at the wheels, right? So in this case, a 1200 CFM unit. You can see, so we have the ERVe-20, it's our 20 cabinet. If we change between the -15 and -30 is our 1.5" versus our 3" wheel. So going with that 3" wheel would actually give us around a 6.5% bump in ERR. So using a higher effectiveness wheel can also help improve those numbers, push that performance, maybe get you closer to being code compliant. And then kind of the last one here is really, I think what the implications of this code is going to mean is we should be considering going with a wheel, right? So I know there's a lot of people using cores out there. I think the struggle is going to be, cores are really pushing the performance. They have to be designed very, very tightly, whereas, we can really hit these numbers pretty easy using a wheel. Because those wheels are more effective, we're also going to have a lower frost threshold, right? So there's a benefit there. And then typically we see lower pressure drop across the wheel, right? So that has a lot of benefits. Lower fan power, smaller motor sizes. The brake horse on those blowers is going to be less. And then, like I said, anytime we're in that greater than 2,500 CFM range, there are a lot of advantages to using a wheel. Typically, we can see a smaller footprint on the unit itself, and then there is usually a cost advantage, so less dollars per CFM on those wheels as well. So that's all I got. So any other questions?
Jordan, I'm not seeing any other questions. We'll wait one more minute if any questions roll on in. But thank you again, Jordan, for your time here. Like I said, this is recorded so we can send this to anyone who needs it. And then we look forward to you join us next week for our makeup air, hopefully. And if you'd like us to do a presentation to your individual firm, we can do that too. Just let us know. Chris, you want to wrap things up too? Anything to add? I think you're muted, Chris.
You'd think after 4 years, we'd know how to unmute. No, Blake, I think you nailed it, and Jordan did a great job as always. I think everyone could tell Jordan's given this presentation more than a few times, and we work with him on a nearly weekly basis and all the intricacies of our particular advanced energy code. I do see a question about the recording being a format that you can send to others. I'm actually posting them on our YouTube page, so it'll be an easy link that you'll be able to forward. So give me a couple of days so I can get it downloaded, do some light editing to it, and just be sure to check Dorsey's LinkedIn, because I'll usually post the links there to the YouTube account, your individual videos. I think that's all I have.
Okay, thanks everyone. Thanks for joining us. We hope to see you next week for Makeup Airs.